So we have one last presentation in this block. This is by Dasha Anderson, recent graduate in cognitive neuroscience from Durham University, where she conducted research into the uses of medical cannabis with the Global Drug Survey. Currently, she works as a research assistant, in developmental neuroscience research, and is about to embark on a PhD in pharmacology and physiology at Bristol University this autumn. In her PhD, Dasha will be studying the psychopharmacology of psilocybin using an integrated approach. As the former chair of students for Sensible Drug Policy UK, Dasha is also heavily involved in youth drug policy activism and harm reduction, and has volunteered with a range of organizations in this sphere, including The Loop and Drugs and Me. Welcome, Dasha. Dasha's talk is titled, sorry, I didn't introduce your talk. Sorry, I should have done that. I was too excited to welcome you. So the title is Psychedelics, Emotional Processing, and the Importance of the Amygdala. So welcome again, officially.
Thank you.
Yours when you're ready.
Perfect. Well, thank you so much. I mean, it's going to be extremely difficult to follow that previous presentation, but I'll do my best. Thank you so much for having me. It's crazy to be around such amazing speakers and all of us. And coming from like a biological perspective, it's actually really interesting to hear about how these kind of things that I'm studying at a biological neuroscience level are happening at the psychological level as well. So that's super interesting. But what I'm going to talk to you guys about today is the role of negative, let me just put my screen on, is about the role of negative emotional processing biases in depression, and how that's related to the amygdala and what psychedelics might be doing to address those negative processing biases and amygdala activation in the brain, and how that might be helping them to work. So I'll just start off by talking a bit about the amygdala. So the amygdala is a brain structure that's really ancient, and it's part of the limbic system of the brain, which is thought to be heavily involved in emotional processing. And the amygdala is thought to have a really important role in allowing us to learn and display emotional responses to emotional stimuli. So in studies where they've looked at people who have had damage or their amygdala has been lesioned, they found that people with those kinds of damage fail to feel fear. So they fail to experience it in their everyday lives. And as well as that, they also fail to recognize fear in other people. So for instance, if they're shown a fearful expression, they're less accurate at identifying that emotion. So that indicates that the amygdala has a really important role in allowing us to detect and experience negative emotions, including fear. So how is that related to depression? Well, a hallmark of depression is negative emotional biases, and these can be exhibited in a number of different ways. So depressed patients often pay more attention to negative emotional stimuli than positive emotional stimuli. They're also better at remembering negative emotional materials than positive emotional materials. And they're also more likely to interpret ambiguous faces, such as people with neutral facial expressions, as negative, so interpreting it as a sad or an angry face rather than a happy face. And fMRI studies, and these are studies that use MRI scans to understand brain activity, they've attempted to understand how these negative emotional biases occur in the brain. And these kinds of studies have actually shown us that people with depression often show increased or stronger responses of the amygdala to negative stimuli. And that's thought to maybe be why we see negative emotional biases in these patients. Maybe their amygdala is just super hyperreactive to emotional stimuli, or specifically negative emotional stimuli. And these negative emotional biases, as you might have heard, are thought to be to do with serotonin. So in depression, there's thought to be an imbalance of the neurotransmitter serotonin. And what neurotransmitters do is they allow cells to communicate with each other. And what conventional antidepressants like SSRIs do is they try and fix that chemical imbalance of serotonin. Now, interestingly, when people who have depression have been given SSRIs, we've actually seen that amygdala hyperreactivity is dampened down in these individuals. So maybe the way that antidepressants work is by damping down amygdala hyperreactivity, which in turn reduces negative emotional bias, allowing people with depression to sort of see the world as it is rather than with a negative lens. So that's some background, but how is that related to psychedelics? So psychedelics and SSRIs or other antidepressants all work on the same serotonin system, but they just do it in slightly different ways. So the way that SSRIs work is they stop cells from reabsorbing serotonin. So that means that there's more serotonin floating around in the gaps between cells, which means they can bind on more receptors and activate more serotonin cells. Similarly, but kind of different, psychedelics like psilocybin directly latch onto those serotonin receptors and activate serotonin cells in that way instead. And interestingly, what we've seen is that psychedelics can actually reduce the processing of negative emotional stimuli. So one example is if people are given psilocybin or LSD, often they show a reduced ability to recognize fear in others. So if shown facial expressions that are fearful, they're less accurate at identifying those emotions. And we also see with psychedelics, obviously, that there's an increase in positive mood. So an interesting question then is whether that effect on mood and depression that we see with psychedelics is caused by a change in negative emotional processing, which maybe is underlined by changes in amygdala activity. So one study aimed to look at this. What they did was they took some healthy participants and had them undergo an fMRI session twice. In one session, they were given psilocybin, and in another session, they were given a placebo. And what they found was that when they were given psilocybin or in the psilocybin condition, amygdala reactivity to negative and neutral stimuli was actually decreased. And the way that they measured this was that they gave participants a task where they were shown two emotional faces presented at the top, and then they had to identify which of those faces matched the emotional expression of another face that was shown underneath it. So as you can see here, activation of the amygdala, which is there, was actually greater in the placebo than in the psilocybin condition, and that was the case for both negative and neutral stimuli, which suggests that psilocybin is doing something to dampen down amygdala reactivity to negative and neutral stimuli. And what's really interesting as well is that that change in amygdala reactivity from placebo to psilocybin actually was associated with an increase in positive mood. So maybe the way that psilocybin is improving the mood of individuals is through affecting the amygdala, reducing amygdala reactivity to negative stimuli. It's all very interesting, but I think that there are some questions that we need to address before we can make that conclusion. So the first thing is that these authors measured amygdala reactivity while participants were in the midst of their acute psychedelic experience, like they were literally tripping in the scanner. And I think a potential reason why amygdala reactivity might have been reduced is that they could have just been too distracted to actually engage in the task, the amygdala reactivity task. We've seen in other studies when individuals are distracted from a cognitive task while undergoing an fMRI scan, the related brain responses are actually dampened down. So maybe that's why we're seeing a dampening down of amygdala reactivity following the administration of psilocybin. Another thing that kind of comes out of this is the fact that this study doesn't really, because it was measured during the high, this study doesn't really tell us anything about the long-term effects of psilocybin on amygdala reactivity. We've seen from clinical trials that psilocybin can have long-term effects on depressive symptoms and mood, but we don't know here if that's caused or that could be underlined by amygdala reactivity. So one study wanted to look at the long-term effects of psilocybin on the amygdala. What they did was they gave healthy volunteers a single high dose of psilocybin, and they had them undergo an fMRI session again 1 day before the psilocybin was administered, a week after, and a month after as well, rather than in the acute psilocybin high. And they used a similar amygdala reactivity task to the previous study. And what they found was that as well as negative mood, amygdala responses to emotional facial stimuli were reduced a week after they had received the psilocybin. And this in some cases lasted up to a month. So this is super interesting because this suggests that the effects of psilocybin on the brain can outlast the acute effects of psilocybin on the body. So we know that psilocybin has a half-life of about 3 hours, and that means that within a week, psilocybin will be eliminated from the body. So this suggests that psilocybin is having some kind of really long-term effect on the brain beyond just its acute effects. And you guys might have heard of brain plasticity, and that's what's kind of thought to be underlying this. So brain plasticity refers to the ability of cells to form new connections with each other. And those new connections are thought to be really important for learning and memory. In the context of depression, that could mean allowing people to regenerate emotional processing patterns. So for instance, unlearning healthy negative biases and learning new, healthier emotional processing patterns. But a kind of another thing that comes out of the study is the fact that amygdala responses were reduced to emotional facial stimuli in general, not specifically negative stimuli. It's both negative and positive stimuli. And that's interesting because that kind of is consistent with more recent suggestions about the role of the amygdala. So rather than being a brain area that's specifically involved in negative emotional processing, one suggestion is that the amygdala is actually involved in detecting salient stimuli, so emotionally relevant stimuli. And obviously that could be a positive stimulus or a negative stimulus. But I think one question still remains. Both of these studies were conducted in healthy volunteers. So I think from these studies, we can't be sure that psilocybin will have the same effect on the amygdala in depressed patients as it will have in healthy volunteers. And obviously, we're looking to treat depression, so we need to understand how it works in depressed people. So one study actually aimed to look at this. So what they did was they gave people with treatment-resistant depression, so that's depression that hasn't previously responded to conventional antidepressant treatment. They gave them psilocybin therapy and measured amygdala reactivity 1 week before and the day after the psilocybin therapy. And in this situation, amygdala reactivity was measured by presenting patients with lots of different emotional faces in series, and they had to press a button every time the face changed identity, so it was a different person, and that was just to make sure that they were actually attending to the stimuli, like paying attention to them. Now, in this study, they actually found that following the psilocybin trip, amygdala activation in response to fearful and happy faces was increased. And that's kind of the opposite of what we saw with the previous studies where it was decreased in healthy volunteers. It seems to be increased in this situation. And what's additionally quite interesting is that the amygdala increases in response to fearful stimuli actually were associated with depressive symptoms a week later. So maybe the way that psilocybin is affecting depressive symptoms in these patients is by increasing amygdala reactivity to negative and positive stimuli. And the authors of this study basically suggested that maybe this is because conventional antidepressants work in a completely different way to psychedelics. So from qualitative research, speaking to people that have had experiences with antidepressants and psilocybin, they found that people who have had conventional antidepressants often describe these drugs as kind of dampening down or blunting their emotions, making them disconnected from their emotions. And maybe that's why we're seeing a decrease in amygdala reactivity in these patients. In contrast, people who have received psilocybin often describe the drugs as increasing their emotional connectedness, allowing them to relate better to their emotions, to confront their emotions, confront trauma. And maybe that's why we're seeing an increase in amygdala reactivity in these patients. And I think that these differences in mechanisms aren't necessarily surprising when you consider that although both types of drugs affect the same serotonergic system, they do so in quite different ways, as I explained before. So what could be driving that increase in amygdala reactivity following a psilocybin trip in people with depression? Well, one suggestion is that it's to do with a thing called functional connectivity. And functional connectivity is something that when we do functional connectivity analyses, we're able to understand how the activity of completely different areas of the brain are related. So for instance, how does the activity of the amygdala, how similar is it to another brain area? And that tells us something about how these areas are connected, how they communicate, maybe how they integrate information. And one area that's quite interesting in this area of research is the ventromedial prefrontal cortex. And that's an area of the brain that sits at the front of the brain. And it's really important for allowing us, or for emotional regulation, so for regulating or controlling our own emotions. And this is thought to be due to its inhibitory or kind of dampening effects on emotional limbic regions, including the amygdala. So as you can see here, it's suggested that the ventromedial prefrontal cortex, through its inhibitory connections to the amygdala, it inhibits amygdala activation. And in one study, which actually used the same data from the previous study, but just analyzed it in a new way, they looked at how psilocybin affected functional connectivity between the ventromedial prefrontal cortex and the amygdala during emotional phase processing. And they found that that link between the amygdala and the ventromedial prefrontal cortex decreased. There was less connectivity, so their patterns of activation was less similar. And they suggested that this might be why psilocybin is increasing amygdala activation in depression. What happens is, in theory, the psilocybin comes in and it disrupts the connection between ventromedial prefrontal cortex and the amygdala. This means that the amygdala is no longer inhibited, it springs into action, it's allowed to do what it is evolved to do, which is respond to emotional stimuli. So what are the take-home messages from all of this information? Well, I think the most puzzling question that remains is the fact that that amygdala hyperreactivity that we see in depression is often described as like a biomarker or a risk factor of depression. It's thought to be what's causing the depression, or at least some kind of mechanism. And so it seems strange that a drug that would treat depressive symptoms would actually increase that abnormal hyperreactivity. It's a bit strange, but I think that this just highlights the fact that in psychology and neuroscience, things are always way more complicated than you want them to be. I think that rather than trying to understand depression through one specific region of the brain, like the amygdala, it's probably quite likely that the mechanisms of depression are spread throughout the entire brain, and that in order to understand and treat depression, we need to consider the role of brain networks and brain systems, how different brain regions are connected and work together. So that's quite clearly here highlighted by the fact that psilocybin disrupts connections between, for instance, the amygdala and the ventromedial prefrontal cortex. And other research has shown alterations to a wider network called the default mode network, which I don't have time to go into now. So clearly we need more research to understand how depression is working in the brain at a distributed level, and also to understand how things like the regeneration of emotional processing patterns might be involved in creating and having depression, basically. And I think that by continuing to study how psychedelics work in the brain in individuals, we can learn more about the conditions that we're trying to treat, or both about the brain normally, so consciousness, things like that, but also when consciousness is interrupted and people have unhealthy processing in their brain. Thank you very much. I'm happy to take any questions. And I'll stop
Thank you,
sharing.
Dasha.
Thank you.
So we have time for one question. So Kim here is asking, it looked like in the post 1 month amygdala reactivity even increased compared to baseline. Do you have an explanation for this? was this accompanied with a subjectively increased fear response?
That's a really interesting question. I noticed that as well myself. I think what's happened there is that they described amygdala reactivity as going back to baseline. So when they did the statistical analyses to see if the difference between each condition was significant, so whether we could say like, yes, this is not just random, this is actually a statistical significant result. I think they didn't find a difference between 1 month and what's the word? And baseline. That makes sense.
And so my question is also, it's probably a challenge for research too, and for all the neuroscience, the data part of it, basically, when you're doing clinical studies, to consider the brain as systems and to measure what the connectedness is, right? That is also a challenge.
Absolutely. I think that's the biggest challenge to neuroscience at the moment. Like it's so much easier to wrap your head around the idea that, oh, well, the amygdala is slightly different, that's what's causing depression. Like that's a really easy concept to understand and try and treat. Whereas trying to treat in things that are distributed throughout the entire brain is a lot more difficult. It's a lot more challenging to think about what kinds of drugs and things you would use to affect that. So I think what's really exciting is the fact that drugs like psilocybin actually do affect the entire brain and might be our key to being able to treat those kinds of conditions that don't just happen in one brain area. I mean, I think nothing happens in one brain area anyway. That's what we're starting to realize.
Yeah, and it seems like also as technology is progressing, the two, that and research, will come together in a very strong way.
Definitely, like we're developing much stronger statistical models that allow us to understand how brain regions work together. Like, for instance, functional connectivity, it was using the exact same data. They were just able to look at the data in a new way. And rather than looking at reactivity of one brain region, they basically just looked at reactivity of two brain regions and then saw how that was associated. So it's just like finding new statistical methods to do that. Yeah.
Cool. Thank you so much, Dasha.
Thank you. Thank you.
It's a pleasure to have you.
Thank you so much.
And with that, we are concluding our first block of presentations. I'm handing it over to Marvin, who is explaining now what's next.
Sure, thank you, Melina. Thank you to all our speakers, to our student speakers, to the keynote speakers. I think this has been an amazing first half of the day that is now coming to a much deserved conclusion. It was very interesting and insightful.